Okay, 7:30. Let's get started. So today we are supposed to review that multiplication division circuit, right? Oh, let me start the recording on the cloud. Just hold on. Okay, yeah. So any question from that lecture, division, multiplication, or previous one? Okay, so I want to show you today a simple combinational multiplier on the Verilog simulation side so that you can possibly pick up that concept a little bit more in detail. Let me share my screen with you. Okay. So I'm talking about this one, right? This faster combinational multiplier. This is like the 32-bit faster combinational multiplier. And it has this 31 adder, 32-bit adder, 31, 32-bit adder connected together with, I think this is 32 of 32-bit AND. And what this one is, let's review this. Like in terms of smaller, like let's try to do a 4-bit 4-bit multiplication scenario, and that circuit is okay. Okay, this is how I did. Okay, one is that first I constructed the 4-bit AND 4-bit AND circuit. It's basically taking the two 4-bit input, and its output is AND of that 4 bits, and instantiated the single 1-bit AND 2 input to 1 output and simply join them, right? We use the 4 AND gate onto this, just join those signals like A0 and B0 to Y0, A1, B1 to Y1 through the AND logic. And that becomes my 4-bit 2-input AND gate. Then I constructed the multiplier with an ripple carry bit, ripple carry addition. For that, remember last day I created this adder circuit. So I added, basically we looked at this circuit last day. Okay, so I kind of took that and just ripped off the subtraction part, like this XOR parts, and directly just make it an pure addition circuit, pure adder, like no subtraction part for here. That's all. So this one I am going to use in this circuit. So what I'm doing here, let's refer to this one. Okay. All right. So you see that this ANDs, basically what at each stages it's doing, it's taking the multiplicand, that 32-bit as it is, and then replicating the multiplier bit 0, that LSB 32 times, then another AND it is replicating multiplier bit 1 with 32 times, and so on and so forth. So for 4-bit cases, I did the very similar thing. Like it's an 4-bit. This is, in this case, this is 32-bit 2-input AND. Now my case, it is 4-bit 2-input and multiplicand. I am passing the multiplicand directly, and I am replicating the multiplier LSB bit 0 4 times, and next stage I'm doing it the first bit, second bit, third bit, and fourth bit, so on and so forth. So replicating that is basically following these logic circuit. So these are those ANDs. So for 32-bit, we had this 32 of these ANDs. So for this circuit, I have 4 bits. So 4-bit ANDs I need there, and I instantiated them. Now here a little bit talking about these wires. So I used like an array of bus. Like these are 4-bit buses, and add out and AND out. This is like I'm trying to capture the output of the adder with the add out and capture output of the AND gates with the AND underscore out. And since there would be like 3 adders and 4 AND gates, such that I used a array of those buses. So each of them are 32-bit in this case, right? For my case, it will be 4-bit output, and I have 4 such AND stages. So that's what the array is. It is just to make the coding life little simpler, nothing else. I can use like different names for different stages. That's also okay. So that's what I am actually connecting here. And out 0 means it's that 3 output what is that? Yeah. And out 0 means it's the already 4-bit bus of that array. And this is also and out 1 is another 4-bit bus, and out 2 is another 4-bit bus, and out 3 is another 4-bit bus. So I'm connecting them. Now about this adder. Now we need to see carefully in this circuit what they're doing for the 32-bit. First of all, in the first stage AND output, the very LSB goes as your like a multiplication result bit. Okay, multiplication result. Then on the adder side, I use rest of the 31-bit prepended with a 0 at the like a MSB position of that adder input. So now look at this line 14, which has the input of the B. I am passing the MSB as 0 and taking the MSB side, your 3-bit MSB side. Okay, so the LSB of the AND out 0, that bus actually used here. Look at that buff. I have used the buffer just for like make it clear. The code is clear. There is no point in using the buffer, but it is just to make my point clear and design clear that this I'm drawing out the AND out 0, that bus's LSB as my result 0 bit, and add okay, and after that I'll come to this add out, etc. But this is what is happening. Like first LSB of the first stage AND goes as a multiplication result bit, and rest of the bit prepended with a 0 goes into the adder. Okay, and then what is the other input? Other input is the AND out from the next AND stage. So that's what the AND out 1 is. Then what are the outputs then going to be? Okay, so adder out is going to be add out 0, and overflow is a CO0. That's a simple wire of array of where that CO is. So that's I'm connecting the CO0 to the first stage adder. Now you see from there first stage adder, what is going on from the result side, the LSB goes as the next bit of output. So you see that line 19, adder out, the first stage adder output, the LSB is connected to the results second bit. So that's what it is going out. And then rest of the result along with the C carry out goes to the next stage of adder. So that's what it is connected. Look at the next stage adder at line 15. The B, that terminal, that bus is connected with the addition output from the previous stage, but we are picking up the 3-bit MSB side and prepending with the carry out from the previous stage adder. That's what it is going. and the other terminal is connected to the AND, the next stage AND's outputs, the AND out 2, and the output of this adder is as a overflow going to the CO1, and result is going out as a add out 1. Now, where this add out 1 is used, first of all, look at this line 20. Add out once the LSB is connected to the result 2, and rest of them are fed into the next stage, adder 2, which is line 16. Like this B is basically add out of the second stage adder, take the 3 bit out of it, 3 MSB side, and prepend with the carry out from that stage of adder. That makes the 4 bit of addition argument or addition operands into that RC in adder 2, and the other operand is coming from the third stage of, or the, it's the fourth stage basically, fourth stage of the and out, okay, and fourth stage. And the overflow is CO2, and our addition result is 2. So how then does 8-bit output, this is 4-bit operand, 8-bit output is constructed. So we all understood so far, line 18, 19. 20 is similar, add stage 1, LSB 0 is the result 2. Result 3 is the LSB of the third stage of adder, first, second, third stage of adder out. And then rest of the 4 bits are constructed out of the rest of the adder, last stage adder output, and the carry out from the last stage of the adder. So that's how this is a sample like 4-bit multiplier, and the same thing, same philosophy happens for the 32-bit combinational multiplier. There we use like 31 adder, and then we actually from each stages of adder and the first stage of AND, first LSB is drawn out as my bits in the result side, and then at the last 31st adder, the entire output along with the carry out is taken as a part of the result, and that makes everything as a 64-bit result out of this. So far so good. Any question? All right, now how it works, let us just test it if it actually results correct output or not. So I think already I loaded that into my simulation. I have these 2 operands, and this is the one, like this is not as pretty as the diagram is, but it is somewhat showing you I have these 4 stages of AND and 3 stages of adder, and they are connected to make through the buffer the result bit, and etc. etc. So if we run these, then let's check. So I have 0 as one operand. Okay, let me just okay, I think this should be enough. So as long as one operand is 0, my result is 0. And then 1, 0 is 0. Okay, let's change the radix. Okay, and then 1 multiplied by that number is result is looking good. 4 multiplied by 1. And let's pick up some random sample, like 9 multiplied by 4 is 36. 9 multiplied by 11 is 99. 12 is 108. Seems good. Let's go to the end. 15 multiplied by 1 is 15, 30, 45, 60, etc. 15 multiplied by 15 is 225. That seems to be correct. So this combinational multiplier is working just fine for us. Question? Okay, so Catherine asked me, can you clarify what is the buff again? And I have one more question. Can you do another example for multiplication and division? Okay, I'll come back to that, Hawk. Catherine, what's the buff again? Okay, so remember these wires like LSBs are going out and making the result. I just put a buffer in middle just to make this code clear, which one is going where. Make sense, Catherine?
Okay, thank you.
Okay. So Hawk, can you do another example on multiplication and division? Uh, what can you like specifically what is bothering you?
I mean how you shift those bit in those operations.
So okay. Let's try that out. Let's try that out. So you're asking about the paper pencil method.
Yeah.
So let's say just an arbitrary this multiplication, right? So we go with the let's say this is my multiplicand and this is my multiplier, and then what we do is basically multiply 1 with this multiplicand and write it down. Okay, and then what we can do, as we seen in the simplified multiplication circuit, we can actually go and finalize this bit. Look at this bit. And the carry out from this whole, okay, we can add a 0 on top of that here. Okay, and then we move to the next bit and multiply it. So that becomes 0, 0, 0, 0, which basically now we add this up 1, 0, 1, 0 with a carry out bit of 0 here. And then I can finalize this bit. And then we move into next bit, multiply with the multiplicand, and that becomes 1, 0, 1, 1. Add them up, which is 1, 1, 1 with a carry 0. So at this point, I can finalize these, and then I move on to this last one, which will give a multiplication result 1, 1, which is 0, 1, 0, 0, 0, 1. 1 as an overflow bit here. And that gives you, so we finalize these as one more bit, 1, 2, 3, 4. And this is 4 more bit, which gives me the answer 1, 0, 0, 0, 1, 1, 1, 1. So let's cross check. What is this number? This is like 1, 2, 4, 8, 16, 32, 64, 128. So this is 128 plus 8 plus 4 plus 2 plus 1, which is 130, 143, right? Base 10. 10, 15. Yeah, seems like correct. And what was this? This was my 1, 2, 4, 8. 11 base 10 multiplied by this is 8, 12, 13 multiplied by 13, which is 3, 4, 1. Yeah, this matches. So is that clear, Hope, or you have on the multiplication side?
Yeah, makes sense.
Okay. Now on to the division is basically uh, let's see. Let's take 4-bit 11 divided by 3. 11 divided by 3. So what will be the result is a key quotient is 3 and remainder is 2, right?
Did you change the slides, Professor?
Oh, sorry. Yeah, so this is the example we are going to do. 11 by 3, all 4 bit. So my dividend is 11, which is like 1, 0, 1, 1. And my divider is 0, 0, 1, 1. So in this process, what we do as a step by step is basically we are bringing this in the scope of this guy, right? So we are first bringing here. So this one is greater than like this is like 100. So I bring down this guy. This is greater. This is okay. Yeah, and no, hold on. 1, 1, 1, 1. Sorry, my bad. So in this paper pencil process, what we want to do 0, 0, 1, 1. So let's just consider 1, 1. So we want to place this 1, 1 in a position from the MSB side that the quantity, partial quantity is greater than the value 3. So this would be like this one, right? We can place it under here. So that becomes your, then we do a subtraction. So that means this quantity is 4 plus 1, 5, and this is 3. So my result is going to be 2, right? And we place a 1 in this quotient. And now we bring down this one here, okay, and do the 5, like same quantity we place it under this 101. This is 5, this is 3, which is like give me 1, 0 as a reminder, and I write a 1 here at the quotient. So that means my, and I stop. Basically, this one is less than the divisor. So this becomes my quotient, which is 3, and this becomes my remainder, which is 2. Make sense?
Yeah, makes sense.
All right. So,
Hey, Professor.
yes.
I was just wondering if you're going to post practice problems for chapters 9 through 11, like all the other chapters, or if we're just supposed to just go off the videos, like there's no particular practice problems for this bit.
These are more like, yeah, I need to think of that. This doesn't have a specific problem except for the like counting the components and etc. and
Right.
and to grab your concept up basically. Nothing from the
Cool.
problem side. Like
Okay.
maximum it is circuit drawing, but in this online scenario, circuit drawing problem, at least from the exam point of view, it's possibly out of question. I'm still trying to like find out some technology where I can, if I can use it to give you a diagram
Yeah.
drawing question through the canvas on this whatever the lockdown browser. Yeah, I haven't found it yet.
Cool. Thanks, Professor.
Okay, let's take 5 minute break then. 8 o'clock, about 8 o'clock, we'll be back. Okay, everyone, let's get started. Um, so, let's do a pop quiz. Go to your canvas and tell me when you are ready to enter the passcode. So I have 64 out of 83 of you said yes, you're ready. Seventy-six, 77. 6 of you need to be ready. 79. I'll wait for another 20 seconds probably till 2 minutes, then I'll move on to the giving the passcode. Okay, so let me give the passcode. Okay, here it go. Probably 1 or 2 minutes for every one of you, or a few seconds. I see. Okay, so I think most of you are done with the quiz. Let's see how did you guys do. Okay. Start. Oh, not good at all. Average is 46%, high score 85. Okay. Yeah, you could do better on that. All right. So now let's do this problem. Uh, we have this 32-bit 32-bit this multiplier, combinational multiplier. Let's count the component on that. Assume that everything is done with a NAND as a basic circuit. So we need to like calculate how many NANDs would be there, how many MOS transistors that means would be there. So number one is basically the hardest problem. From there we can derive number of MOS transistors. And then it's if each transistor takes a 10 nanometer by 10 nanometer space, then how much area this circuit will contain. So spend about like 5 minutes yourself, then I will open up the breakout room for you guys to discuss as a discussion as a group. Then we can discuss the solution of that.
Hey, professor,
Yes.
when you say all NAND, does that mean NAND and an inverse or a not operator too?
It's all with the NAND gate
So you,
implementation.
okay, so you can do an adder with just NANDs, no
Yes.
knots needed. Okay, got it.
And it's just a adder, by the way, no, not the subtraction addition, just a pure adder.
Got it. Thanks.
Okay, I'm opening up the breakout room for you for discuss within your study group for this. So let me open the room for all for 10 minutes and then we will come back. Okay, I realized I was in mute. I believe all of you guys are here. So who wants to go for the answer or explain something? Which group? Let's see. Any volunteer?
Our group got an answer we were pretty satisfied with.
Sure. Yeah, why don't you explain at least?
Cool. So for each adder, it's basically just the same as a full adder without the XOR, right?
Right.
So you just take the amount that we found yesterday and subtract the amount in XOR, and then you end up with the amount of NAND gates per adder to be 480.
Okay.
And then you have, because you don't have an adder for the first bit, because you're just or sorry, you don't have you're not doing a you're not doing a multi, you don't need an adder for the first step, so you only need 31. So you do 480 times 31, and that handles the NANDs for the adders. But then for the ANDs, those are basically just two NANDs together, and each one has two, and then there are 32 total. So you end up with, you just add 2 times 32, and you end up with 14,944 NANDs there, and that's the answer to the first bit.
Okay.
And then for the MOS, you just you know that it's 4 times, or whatever amount of MOS that are in a NAND gate. I think it's just 4, right? Yeah. So it's just 4 times that, and you end up with 59,776 MOS transistors. And then for each transistor, you multiply it by 100 nanometers squared, and you end up with an area in nanometers squared, which you can unit convert to micrometers squared, and we ended up with 5.98 micrometers squared.
Yeah, seems to be legitimate. Anyone else who wants to have a different opinion about these steps and answer? So basically what Frank did is practically picked up the count we did last day, this 32-bit triple carry adder. Since it is pure adder, we don't need to add this extra XOR there or overflow bit, anything like that. Just this is 480 NAND. And then we need, so each adder is 480 NAND. So we need 31 adder in this circuit, 32-bit combinational multiplier circuit. So that is 31 multiplied by 480. And each of these 32-bit 2x1 AND has basically 32 AND gate in it, right? And each AND gate is combination of 2 NAND gates. So this is basically 64 NAND gate at one of these component. And we have 32 such components. So it is 32 multiplied by 64 NAND, add up with this adder NAND, all together, you get total number of NANDs in the circuit. And each NAND, if you recall the NAND structure in the CMOS technology, it has 4 MOSFET, 2 PMOS and 2 NMOS. So it is total of 4 multiplied by that number, that becomes number of MOS transistor. And let's assume roughly if each MOS transistor is needed 10 by 10 nanometer square space, you multiply that number of MOS transistor with this space to get a nanometer square result. And if we want to do it in the micrometer square result, we can convert the unit accordingly. Is that clear for everybody?
Professor?
Yes.
Do you have a diagram in one of your slides showing them that there's 4 MOS transistors in a NAND gate, or is that just something that's given?
Come again, Akash, I didn't follow your question.
I said, do you have like a diagram in one of your slides or something showing how many MOS transistors are in a NAND gate, or is that just given?
It's in the diagram. in the NAND gate. That is a standard structure for the CMOS technology.
Okay.
So it's two PMOS and two NMOS stacked up.
And sorry, Professor, I want to make sure I understood and that we actually did it right. Were you saying that there are were you saying that there are 64 MOS per AND
No,
gate? Or were you saying
no, 64 NAND.
there are
But of
60? Wait, what? Oh, right, because it's 32-bit. Okay.
32 bits, right? So 32 and each and
Right.
two NAND. So this basically 64 NAND. This 32-bit AND contains 64 NAND, means multiplied by 4, that many MOS. But we don't need to multiply at this point, right? We add up all the NAND gates needed, then multiply with 4. That becomes like number of MOS transistors, and then we basically take the area. So just to note on the whiteboard, so that you guys all can refer to it. So what all we are doing, these guy, each of them is 480 NAND, and this one is 64 NAND, each of them, right? So total we have, that means 31, because this series has 31 adder and 32 bit AND, right? So that means my total is 31 multiplied by 480 plus 64 multiplied by 32, that many NANDs. So that many NANDs. Now if you multiply that quantity, whatever X, multiplied with 4, that is that many NMOS, or sorry, MOS transistors, X for transistors, then area is basically 4 into X multiplied by 100 nanometers square. So that becomes the area of this component. Okay. Yes.
You explain why there are 64 NANDs per 32-bit AND again?
So this one, so how do you make, let's say, 4-bit AND? Like 4-bit, 2 operands, A0, A1, A2, A3, B0, B1, B2, B3, and basically it is 1 AND, 2 AND, 3 AND, 4 AND. So far so good. We all agree it has to be at a 4-bit AND gate, has to have a 4 AND gate inside it. So that means 32-bit AND has a 32 AND gate in it. Now what is a 1 AND gate? NAND and a NOT, right? So this is a AND gate basically, right? So that means 64 NAND gate for these guys. For 4-bit AND it will be like 8 NAND gates, isn't it? Make sense?
Yes, thank you.
Okay, so if there are no more questions, let's conclude today's class. Remember, next day or this week after this lecture, we are going to start on this core part of the computer architecture, and we'll start with the how we actually made and implement a processor. Now we know about all the components like these registers, flip-flops, all these logic gates, multiplexer, decoder, ALU, etc. Now we try to place them together to build up a microprocessor from scratch. So that would be the first real computer architecture study for you guys. So please pay attention. That is very important concept. And we'll spend on that specific lecture, lecture 11, 2 days. Like next week, there is no other lecture. Only lecture 11, we'll spend, make it like 2 days. One day we'll go through the half of that, and another day go rest of the process, rest of the steps, so that you can space out your study and sink into the concept of putting together a microprocessor. Okay, so please review them, and yeah, and we'll see you on next week then.